All right, so with our derivative function, 1 over 2 square root of x minus 2, we can again calculate the slopes at any value of x we want, the instantaneous rate of change, the slope of the tangent line, and we do this so often we end up taking it for granted. And maybe in today's days and age, yeah, I mean, the wheel once was considered an awesome invention, and we take that for granted too. So 6 minus 2 is 4, square root of 4 is 2, so we end up with a fourth. And then at 16, f prime of 16 is 1 over 2 the square root of 14. That's an awesome number, right? That doesn't really work very well. 27. You know what? Let's change it from 16 to 18. I think that's probably what I meant. Let's say what I meant, and not what I actually said. That'll be 18 here. And now we can get a nice number out of it. That's 1 over 2 times 4. That's 1/8. And then instead of 27, let's do 29. And we get f. Oh, it sure does. Yeah, you're right. I was trying to get to 27. Yeah, 27 works. Thank you. So that gives you 1 over 10. So if you remember, we said at the beginning, yeah, we already did 2. It's done fine. We said at the beginning that the y values were increasing at what rate? Decreasing rate. So you can see here that they are getting bigger. The slopes are positive, but the slopes are getting water. Smaller, 1/4, 1/8, 1/10. So there's an indication that the function is increasing at a decreasing rate. Describe the values of x for which f is continuous. Well, the function is continuous over its entire domain, and the domain is what? Everything, yeah, 2 included, right? So it would be for all x greater than or equal to 2. What are the values for which the function is differentiable? That is, what values of x does the derivative exist? Yeah, non-inclusive. Very good. We just saw that. So that's going to be typically the case. You're going to have a domain of a derivative that is either the same size as the original function, and that's going to be true for like polynomials, or in this case, it's going to be smaller. It's never going to be larger. And this one was because of a vertical tangent line. All right, so here's another thing that we're going to be doing quite a bit this year. Write the equation of the tangent line in Taylor form for our function at x equals 27. So let's just change this to 27. I want to write the equation of that blue line right there. So there's lots of different equations of lines. We're going to use Taylor form throughout the year. And Taylor form is real easy. If you remember your point slope form, your point slope form was y minus y sub 1 equals m times x minus x sub 1. And that really just comes from the definition of slope. M is the change in y over the change in x. So the only difference between this and Taylor form is we add the y1 to both sides. So here's the Taylor form that we're going to use. Y is equal to y sub 1 plus the slope times x minus x sub 1. That's Taylor form. And Taylor is named after a guy named Brooke Taylor, who at the end of the year, when we learn Taylor polynomials, you'll see why this is called Taylor form. He writes his polynomials in increasing order, essentially. So we have y sub 1, which is the constant, and then we have plus the slope times x minus x sub 1, which is going to be x to the first, and then we'll have later on x squared, so on and so forth. So that's Taylor form. It's already solved for y, which is good, because if we ever wanted to graph these in our calculator, Taylor form is ready to go, okay? So there's Taylor form. Memorize it. We'll be using it quite a bit. Let's go ahead and write the equation then. So I'm going to put EQ for not equestrian, but for equation. Labeling what we're doing, we get y equals. Do we have the y value at 27? Well, not yet. So let's go ahead and find it. Remember, f of x is still going to be your y value machine. And that's the square root of 27 minus 2. That's 5. So we have the ordered pair 27, 5. So 5 is the y value, so it's going to be 5 plus the slope. We already found that, didn't we? It was up here. It was 1/10. 1/10. And then times x minus the given x value is 27. And then you stop. If you're ever asked to write the equation of a line on a free response and it doesn't specify, you can do this and get out of there, right? Taylor form, get out of there. If you needed to put it into slope-intercept form, course, you could distribute the 1/10 and write it as mx plus b. There's another thing that they might ask you. Let me throw this one at you. Sometimes your answers on a multiple choice are in what's called general form, which is this: ax plus by equals c. And then a and b and c are not fractions, they're integers. So if you needed to get an equation of a line and you noticed all your answer choices were in general form, you would still create the equation this way: the y value plus the slope times x minus the x value, and then you just convert it. So if you ever have a fraction like we have here, the first thing you're going to want to do is probably multiply both sides by 10. Okay, so you do the whole thing over here by 10, you multiply this side by 10, and you get 10y equals, and then when you distribute, you get 50 plus, now why did I multiply by 10? Because there's that fraction there, right? So 10 times a tenth is 1, and now there's nothing to distribute, and I get x minus 27. So you basically multiply both sides of the equation by the LCM. And since I only had one fraction, 10 was the denominator. And now we just get everything on one side. So if I, let's do this, 10y, let's do equals 50 minus 27 is 23 plus x. I'll bring the x across. Negative x plus 10y equals 23. That's one version of it. And of course, if that's not there, what could you do to both sides? I mean, you can multiply both sides by any number, really, but if that's not there, chances are multiply both sides by a negative 1. X minus 10y equals negative 23. That would just be you collecting your variables on the other side. So typically, your answer choices are probably not going to have a negative leading coefficient, from my experience. So both of those would be correct, though. Those are the same equation of the line. They're just in general form, right? All right, cool. So we got a lot done on that one. Comments, questions on the derivative? This right here is a handy-dandy tool. Jack Fisher refers to some magical way to find it in the future, but the future isn't here yet, right? All right. So there is another way. There is another way. I'll show you all later. Okay. Right now, I want you to appreciate this method. So there's two other versions of the derivative. Okay. This one is called modified form, and the only difference between modified form and the original definition is instead of this x right here, we replace it with an actual value of x, a number. Okay. And so in that sense, it's kind of less useful, really, because it doesn't give you a function of x at the end that you can then plug into after the fact. You're plugging in an x value beforehand, and you're getting a numeric slope instead of a function. So it's kind of a disposable version. If you only wanted the slope at one point, you can plug it in here and get a number. But if you wanted to find the slope at another point, you'd have to set up the limit and reevaluate it. So it's better to get the function first. But there is a modified form, and that's all it is. It's f prime of c, where c is some arbitrary x value. H goes to 0, c plus h minus f of c over h. Now, you're not going to have to set this up and evaluate it down the road, but what you're going to have to do is recognize that as being set up and interpret that as the derivative of something. Okay, but for now, let's go ahead and set it up and then evaluate it. We'll practice our limit. So we have this function here, x over x plus 1. Notice that x cannot equal negative 1. See that? It's not in the domain. Do you think the slope is going to exist if the function value doesn't exist? Probably not, no. So chances are the derivative, if it's worth anything at all, is also not going to be defined at negative 1. We shall see. Well, actually, we shall not see because we're not doing that. We're finding f prime of 1. All right, so instead of finding f prime of x, we're going to find a slope at 1 directly. So here's what we'll write. F prime of 1 equals, it's still the limit as h goes to 0 because that's the distance between the points. But now it's f of 1 plus h minus f of 1 all over h. So again, all we're doing is replacing x with 1. We're going to use it one time. It's a disposable version. So in the top, we're going to replace x with 1 plus h. It becomes 1 plus h over 1 plus h plus 1. And then minus f of 1 looks like it's 1/2. And all of that is over h. All right, well, notice in the denominator, 1 plus h plus 1, we can simplify that to 2 plus h, or h plus 2. So I'm going to go ahead and just, so I don't have to write a whole other line, I'll just call that 2 plus h. All right, so now if you plug in a 0, you're going to get 0 over 0, which at this point means you set it up correctly. Well done. So what method did we have for eradicating this one? Lick-em, right? Lick-em over lick-em. So your denominators are 2 and 2 plus h. Their LCM, remember m is for multiple, is their product, 2 times 2 plus h. Some people want to add those there. It's LCM. So when you distribute, you're going to get 2 times 1 plus h minus the quantity 2 plus h when the 2's divide out, all over 2h times 2 plus h. And again, the next step here, as we've already seen in 1.4, is to expand it out, 2 plus 2h minus 2 minus h. We bring everything down, and this should be the last line. Everything should work out here. The 2 minus 2's are gone, and we're left with 2h minus h. I'll write it one more time. 2h minus h is 1h. And all that hard work, what happens to the h's? They divide out, leaving you 1. So we got rid of the 0 over 0 problem, and now we plug in. And I'm going to bring it all the way around here. F prime of 1 ends up being, when I plug in the 0 for h, 2 times 2, I get a 4th. So there it is. That's called modified form. It still has the h in it from the definition, but it's the disposable version. Okay? If we wanted to find the slope of this function now at 2, we'd have to go all the way back to the beginning, set up the limit, lick them over, lick them again. So in the interest of finding multiple slopes, you would probably want to use the definition, get your function of x on the back end, and then it's just plug and chug. All right, so what are you going to be expected to do? You're going to be expected to look at something like that and recognize that as a modified form. Okay? And the giveaway is going to be this right here. We typically reserve the use of h going to 0 for the derivative. Okay? So if you ever see the limit as h goes to 0, it's going to be a derivative of something, because we have a lot of different limits. Okay, now let's do this. It says find the equation of the normal line. So we're kind of throwing in other stuff here. We need to know what the normal line is before we can write its equation. Anybody know what the normal line is? I know some of y'all know what the normal line is. What is it? Perpendicular, yeah. So like in physics, when you have your old inclined plane problems, right? You have a block sliding down an inclined plane. You've got gravity. But you also have this force right here, which is called the normal force. And the normal force always works perpendicular to the surface. So kind of the same thing here. The normal line is perpendicular to the tangent line. The normal line is always perpendicular to the tangent line. So a radius in a circle would be a normal line or normal to the tangent line. So now we need to figure out, okay, I know how to find the tangent line slope. That's the derivative. Once I have the tangent line slope, how do I find the perpendicular slope? How are perpendicular slopes related? Opposite or negative reciprocal, whatever you want to call it. Opposite reciprocal or negative reciprocal. Same thing. Yeah, change the sign and flip it. Change the sign and flip it. Their product is -1. Okay, so we already found f of 1, if you remember. F of 1 was 1/2, so we have the ordered pair at 1, 1/2. And now the slope, we already found the slope to be 1/4. So let's go ahead and write the normal slope. I'll write it like this. If you do an upside down capital T, that should be the geometric symbol for perpendicular. Or you could do m sub n if you want for normal. So if the tangent line slope is 1/4, what's the normal slope? -4 over 1, or -4. Good. So now that we have the normal slope, and we have the ordered pair, so we're going to use the same ordered pair. We write the equation of the normal line. We'll do it right here where we have all our ingredients. So remember, in Taylor form, it's y equals, the y value goes next, which is a half, plus the slope. We always add the slope. The slope ends up being a negative number, though. That's the thing that a lot of people mess up. They always think it's minus the slope, so they change the sign. It's not. It's plus the slope, and then it's x minus. That's the only minus right there, x minus the x value. There you go. And you don't have to distribute it or anything. You're done. That's the equation of the normal line. Opposite reciprocal of the tangent line. All right, so good so far, so good? We're already kind of past the wow moment, right? The evolution of it. So now we're kind of in the practicing moment where we're just practicing using it. All right, so to reiterate, this column over here is algebra. Doesn't require calculus. The following are equivalent between 2 points A, f of A, and B, f of B. The slope of the secant line. This thing here, which we call the what? The difference quotient. I'll just put DQ. Oh, blizzard sounds good right about now, doesn't it? Yeah, after lunch. And the average rate of change on the x interval from A to B. They all mean the same thing. Difference quotient, average rate of change on the interval, and the slope of the secant line, they are all the same. Okay? So it's pretty easy to remember that average rate of change doesn't require calculus. It's algebra. Algebra, average, right? They both have that annoying laugh sound. Does that help y'all remember? It should. We're going to be learning how to find derivatives, and later in the year I'm going to say find the average rate of change. And you know how many people are going to take the derivative? No. If it's average rate of change, it's what? Not calculus, but? Okay, y'all, yeah, that's fine. You don't have to say it so annoyingly. Good. This is calculus class after all, so let's go to column 2. This is calculus. At a single point, 1 point, calculus. The following are equivalent. The slope of the tangent line. This fella right here, right? That is the modified form that we just learned. That's the modified form. It gives you a numeric slope, not a function of x, a numeric slope at a specific point. Of course, that is also called f prime of c, which we can read as the derivative at x equals c, or the derivative of f at x equals c. And of course, it's not the average rate of change, but rather the instantaneous rate of change at x equals c. Now you're going to see later on, we're going to drop this right here. We're going to drop the instantaneous part. We're just going to say rate of change at x equals c. How would you know that that still implies instantaneous? Very good. It's at a single point. At a single point, you can add in time, right? And that would refer to a single what? Instant. A single instant, a single moment in time. I don't know how to remember that. There's nothing like instantaneous calculus, they don't have that. There's nothing annoying about that, okay? But algebra, average, rate of change. Got it? 2 points, algebra. 1 point, calculus. No longer a problem, right? No longer a problem. Are you going to play back this video at home for your parents and say, here's my annoying calculus teacher? Just listen to him. Algebra, average. How do you tolerate that guy? All right, how much time do we have left? 6 minutes. Okay, good. So remember I told you that down the line, you're probably not going to have to set this up and evaluate it, but rather you're going to have to recognize it and deconstruct it. Okay? That's what the next example is. Each of the following represents the derivative of some function f of x at some particular x value. Identify the function whose derivative this represents and the x value that it's the derivative at for each one. Okay. You walk up to the problem, you're like, what's up, limit? H is going to 0. When you see H going to 0, that's a red flag, right? Not a red herring, it's a red flag, which signifies that it is a derivative of something, yes? How can we then extract the function from here? this must be f of c plus h minus this must be f of c. Can we infer the c value from this format? It should be 2, right? And can we infer the function? Yes. Here's the way I recommend you learn it. Not to continue to be annoying or anything, but if you look at the first term, wherever you have parentheses and you see 2 plus h, just say, I don't like you 2 plus h. I don't like you 2 plus h. And exit out. Exit out. I don't like you. What do you do to things you don't like? You X them out. Not people, though. Don't do that to people. But things, right? And by Xing out your number plus h, what now are you staring at? Literally, 5x, you're staring at an x, right? 5x squared minus x plus 7. Guess what the function is? This represents the derivative of that function at what x value? Now, this might not be in this pretty format. They might actually simplify that number. So everything you're going to need to reverse engineer this is going to be in the first term. So now, hopefully you didn't obliterate it. You just X'd it out. And now you can peek underneath the X and see that that is a 2. Okay? So this is the setup in modified form for the derivative of this quadratic at x equals 2. And if you want to confirm that, go ahead and set it up yourself, right? We would take the limit as h goes to 0 of f of 2 plus h, and we would plug in a 2 plus h for x, so on and so forth, and you'll see that it is in fact. Okay? So with that in mind, you do now this one. And if you want to say that out loud, you can. If you want to say it in your heart of hearts, it's fine. I don't like you. I want h. Are you actually computing it? Yeah. We don't actually have to continue computing this one, because what's going to happen is if this were a multiple choice question, your answer choices would all be, it's this function at this x value. It's this function at this x value. And if it is a number, if they do want the actual slope at 2, as Jack already said, there's going to be a faster way to get it, which we'll learn soon enough. And we're going to find it that way instead of the sledgehammer. So anyway, Jack is a prophet. He sees the future. He's right. Okay, so if you look at this one, you see h going to 0. You know it's the derivative of some function. I don't like you pi fourths plus h. There it is. It's the first term. So the function whose derivative this must represent is tangent of x, and it's evaluated at x equals, peek underneath there, pi fourths. Yeah, that's the derivative of tangent of x evaluated at pi fourths. So that minus 1, that must be the function evaluated at pi fourths, right? What is tangent of pi fourths? 1. Yeah, so like I said, that last part is not always going to be set up so pretty that you could just extract it from there. It's usually going to be evaluated because it will be a constant, but that's why it's 1. All right, do this one. Identify the function whose derivative this represents and the value of x at which it represents it. Good. I know when saying that out loud, maybe it's annoying, maybe you don't need it, but it's really not very Rachel's challenging to do that, right? I don't like you pi plus h. You're staring at e to the x, that's the function. And of course, then the value of x, which is c, I guess we'll call it, is pi. So that's the derivative of e to the x evaluated at pi. All right, let's do this one together. Where's the second term up there? I don't know. But I don't like you 1 plus h. Let me get my hatred out first. So this function is the natural log of x. And it must be evaluated at x equals, peek underneath there, it's a what? 1. Oh, so this must be the natural log of 1. What is the natural log of 1? 0. Awesome. Perfect timing. We'll pick up on example 7 tomorrow. Be ready for a quiz. You always are. And good luck to those y'all at the pep rally tomorrow. Yeah, yep. Handlers, Blue Crew.